Hello all, welcome to KT Semicon Self-Based Learning Program. In this particular session, we are going to discuss about all the basic logic gates in digital. So let me share my screen. So we are going to have different logic gates in digital design. The very first logic gate which we are going to discuss is a simple NOT gate. Now, your NOT gate is going to have a symbol like this. This is nothing but your NOT gate, where you are going to give an input over here and you are going to get your complemented output over here. Okay. This is a simple NOT gate. Let's say if you are going to give 0, you are going to get 1, and if you are going to get 1, you are going to give 0. This is nothing but your NOT gate. Now, next gate which we are going to have is a simple AND gate. Now, what is this AND gate? Let's say for your 2 input AND gate, you are going to have 2 number of inputs and only 1 number of output. Now, if you are going to, and this is your truth table of your AND gate, A, B, and Y. So if you are going to apply 0, 0, then your output is equal to 0. 0, 1, your output is equal to 0. 1, 0, your output is equal to 0. 1, 1, your output is equal to 1. So if any one of the input is equal to 1 of your AND gate, then your output is equal to 0. If both the inputs are equal to 1, then only your output is equal to 1. That is nothing but a 2 input AND gate. We can also have more than 2 inputs, like 4 input AND gate, where we can provide A, B, C, and D. And this is my output. So this is nothing but my AND gate. Now, next I am going to have OR gate. Now, this is how your OR gate is going to look like. This is a 2 input OR gate where you are going to give 2 inputs A and B, and you are going to get your output Y, which is nothing but A plus B. Okay. So this plus symbol you are going to use for representing your OR operation, and for AND operation you are going to use a symbol dot. Okay. Now, this is your truth table of your OR gate, where if you are going to give 0, 0, you are going to get your output as 0. But if you are going to give your input as 0 and 1, you are going to get your output as 1, 1, 0, your output is equal to 1, and 1, 1 also your output is equal to 1. That means if any one of the input of your OR gate is equal to 1, then you are going to get your output as equal to 1. Or else if you are going to get your output as equal to 0. If both the inputs are equal to 0, your output is equal to 0. This is nothing but my OR gate. NOT gate we have already discussed. Next is NAND gate. If I want to build a NAND gate, then I am going to cascade a simple AND gate and a NOT gate like this. Then I can bring up a simple NAND gate like this. So a NAND gate is nothing but AND gate with a bubble symbol at the output. Now, this is your Boolean expression of your NAND gate. Y is equal to A dot B the whole bar. And coming to the truth table of your NAND gate, this is how your NAND gate truth table is going to look like. If you are going to apply 0, 0, your output is equal to 1, 0, 1 output is equal to 1, 1, 0 output is equal to 1. But if your inputs are 1, 1, then your output is equal to 0. That means for a NAND gate, if both the inputs are equal to 1, your output is equal to 0. But if any one of the input is equal to 0 or both the inputs are equal to 0, your output is equal to 1 only. But both the inputs are equal to 1, your output is equal to 0. That is nothing but my NAND gate. Now coming to my NOR gate. NOR gate is nothing but a cascaded correction of my OR gate and NOT gate. So this is how your NOR gate logic diagram is going to look like, with a bubble at your output. And the expression of your NOR gate is nothing but Y is equal to A plus B the whole bar. And you are going to give your inputs as A and B as 0, 0, 0, 1, 1, 0, and 1, 1. And you can see, and only in the first case, you are going to get your output as 1. That means for your NOR gate, if both the inputs are equal to 0 only, you are going to get your output as 1. But if any one of the input is equal to 0, then your output is equal to 0. Or if your any one of the input is equal to 1, your output is equal to 0. Okay. Now, this is nothing but our NOR gate. Next, we are going to have something known as XOR gate. So this is how your XOR gate is going to look like, and the expression of your XOR gate is nothing but A XOR with B. And if we expand this, we are going to get A bar B plus A B bar. This is the expression of our XOR gate. And this is a true table of our XOR gate, where if we give both the inputs, we are going to get 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. That means if both the inputs are unequal, then we are going to get our output as 1. But if both the inputs are equal, then our output is equal to 0. This is nothing but my XOR gate. Next, I have something known as XNOR gate. Now, coming to my XNOR gate, this is the expression for my XNOR gate, A bar B bar plus EB, and this is a symbol of my XNOR gate. Now, if both the inputs of my XNOR gate are equal, then only I am going to get 1. But if both the inputs of my XNOR gate are unequal, then I am going to get my output as equal to 0. This is nothing but my XNOR gate. So that's all about this particular session, and in our next session we are going to discuss about building simple logic gates using our universal gates. Thank you.